Okay, a very good evening to you wherever you are. It's evening here for us, but greetings to you where you are. And thank you so much for joining us on this fourth session of the second series of our webinar. This is the Nigerian Society of Engineers, Glasgow branch, Scotland, United Kingdom. And we're very happy that you've been able to join us today on this webinar session. As always, it promises to be a very informative and educating session, and we have an expert in the house to discuss with us this excellent topic displayed right now on your screen. I'll be inviting the chairman shortly for his opening remarks, and thereafter I would read the bio, a very brief bio of the speaker, and invite him to give his talk. You'd have opportunity to send in your questions, and the speaker would answer them as well, but you can use the chat box even while he's speaking to send in your questions, and you can raise your hand when the time comes, and my colleague will take you up with the speaker to take care of the questions. And thereafter, we'll have some announcements and make a close. My name is Emmanuel Salifu. I am the publicity secretary of the branch, and it's with great honor and privilege that I welcome you. And at this point, hand over the microphone to the chairman for his opening remarks. But before then, just some housekeeping. Endeavor to keep your microphones mute throughout the session. And I think we'll be having this session for an hour or 2 hours or thereabout. Feel free to observe the health and safety of walking about, stretching yourself, and not being in one position for too long. You know, we get used to these things with the season that we are in. And hopefully all of this will pass on with time. So I'll be inviting chairman of the branch, engineer Dr. Oluseun Adediran, for his opening remarks. Mr. Chairman, over to you.
Oh, thanks, Dr. Emmanuel Salifo. Thanks everyone for joining us today. Just a kind of health and safety side. We all know that the pandemic is still around. We are getting there to get over it. And I just want to say that if we need to move around at any time during the webinar, it's going to take some time. Please feel free to do so. And this is our is really important to everyone joining us today. And also, we as a branch, we want to use this opportunity to express our condolences and to sympathize as well and with the royal family, and our thoughts and our prayer are with the Queen as she mourns the death of the Prince Philip's and her husband. May so rest in perfect peace. We are, you know, it's a marriage of 73 years, so we can understand and the pains that she may be going through just now, and even everybody has been talking about its impact in lives and all that. So this is one of the reasons why we are doing this, to let people know as well that whatever the contribution we can make from every corner of the world, we are connecting from. Let's do it. It's just the time just fly before we know. I also want to recognize the former NSC Vice President, Engineer Mrs. Ogunlano. She's here with us just now. Towards the end, we'll call you to give us your goodwill message, man. And also with us here, we have professor. He's a professor at the same time. He's my dad. He's a role model to every one of us, Professor Ofi. And he was a former Deputy Vice Chancellor of University of Ibadan at the time. And this is people that a lot of us we just want to be like them. So the Prof is joining us at this time. We appreciate you, Prof. And also want to recognize Dr. Mrs. Sophia as well. Thank you, Ma, for joining us. We appreciate you taking time to, I'm sure that even for you to join us tonight, or Ayo will be on his toes, and we really have to deliver. Thank you, Ma. Thank you, sir. If at any time I've not recognized any of the NSC executives, and I also want to recognize the Manchester Public Secretary, Engineer Patrick Ibidoyin. thanks for joining us. And all the NSC Executive Expo, wherever you are joining us from, we really appreciate you. We believe that by the time we finish this webinar today, I mean, every one of us must have had one or two knowledge to what we know before. Thank you so much. I don't want us to waste time because we are a branch that we're always conscious of time. So I'm going to hand over back to Dr. Emmanuel Sali for just to continue with the program. Thank you.
Thank you very much, Chairman, for that remarks. And we welcome all the dignitaries that have joined us today. Really proud and honored to have you in our midst. So I'll be introducing the speaker for his presentation right away. Our speaker today is Ayo Ofi. Ayo Ofi is the Global Discipline Lead, Production Solutions with Baker Hughes Reservoir Technical Services Group. And he is a chartered engineer with the Institution of Mechanical Engineering. He has an MSc from the University of Manchester, an MSc in Environmental Engineering. Ayo is focused on driving the development of integrated reservoir-centric integrity and production solutions, which maximize energy output and value while minimizing long-term environmental impact. This is a particularly interesting one for me. I'm also an environmental engineer, so I welcome my colleague and the speaker for today, Ayo Ofi, as he presents his talk. Over to you, Ayo. I'll stop sharing.
Thank you very much. Thank you very much, Emmanuel. And thank you, Dr. Sheung. I'm really honored to be able to give this talk today. And I do not take the matters of energy and the environmental aspect lightly at all. My talk today is centered around the automation and artificial intelligence and the roles it plays in the performance and environmental impact in the energy sector. But because, again, we're speaking to Nigerian Society of Engineers, I would be focusing on today's topic on the oil and gas industry for now. And I will touch on a few energy transition topics, just peripherally, but mainly focused on the Nigerian oil and gas sector. So as Emmanuel has said, I started off with a bachelor's degree in mechanical engineering, where I met Dr. Sheung, and then I went on to study environmental engineering. And I've tried to marry those two disciplines in a lot of the work I've done. So I started off with Adax Petroleum, which is then was a Swiss-owned oil operator in West Africa and in the Middle East, where I started off as a production technologist, moved into a reservoir engineering role. And from then on, I moved into a reserves evaluation role, which landed me my next role within Gaffney, Klein and Associates. And for those who don't know Gaffney is a reserves evaluation and certification body. Reserves for an oil company is almost like your bank balance. It shows your profitability, it shows how much you have left. It can help, place a value on the assets and the company as it is. Soon after, Gaffney got bought over by Baker Hughes, and then I found myself in an oil service role, but still in the subsurface discipline. So I work within Reservoir Technical Services, which is the subsurface arm of Baker Hughes. And again, at the moment, I'm Global Discipline Lead for Production Solutions. So we're working on integrated production solutions, and actually I have a project now which is quite related to this topic. I'm married, I've got 2 children, and on the call with me today, as you know, I wasn't sure if you had enough numbers, so I said I'll just call my mom and my dad and make sure that we can make up the numbers. So my interest is in food technology and fitness and music, and I am quite passionate about my family and my health. So I'll dive straight into it. This is the presentation outline. We'll start with presenting a statement of the challenge. Every engineering solution should be focused on a challenge, not just for research purposes or just for doing sake. Implications of us not doing anything particularly for the Nigerian sector, and then talk around the digital transformation within the oil and gas, focus on the upstream, and then focus on the production operations portion. Now, I mentioned production operations because we're in a dip in the oil industry, and at the moment, exploration and appraisal, expansion, improve recovery, all that's on hold. So most of the operators and most of the industry is focused on maintaining current production and seeing how they can get the best value for every dollar spent. Then I will focus on failure analysis for one of the aspects of production operations and how we can minimize that, and then relate it back to where we are in the industry and segue into a discussion about what we need to do, and then open up for discussion. So first of all, despite the diversification of oil, fossil fuel consumption over the year, and all the energy transition initiatives that have been going on, we see that oil and gas is still playing a huge role. And I would argue that it's still going to play a huge role in the nearest future. However, there's no secret that, in the energy supply industry, it's largely driven by things outside the industry's control. So political stability, when there's war, the price goes up. When people are shut down here, economic stability, Venezuela goes into trouble, we lose production from there. Stakeholder pressure, you have OPEC, trying to control the price, and other people trying to avoid that hold. And then you have competition from other energy sources. So in the recent times, in the West and in the Far East as well, you see a lot of subsidy for renewable energy, what's called renewable energy. So we're talking about hydrogen, we're talking about gas storage, we're talking about geothermal, hydropower, all that sort of stuff. And they are in direct competition with our oil and gas sector. And then the other thing is the fact that you see here that we had an oil and gas crisis in 2008. We had one, I think the one before 2008 was probably in the maybe 1991. Then we had one in 2006, and we're having one now. So there's beginning to be an increase in the frequency of this crisis. What's going to happen next, nobody knows. But we just need to ensure that we are resilient and we can take this industry forward to ensure that one of the cash cows within our country of origin is protected. And we help transition into the cleaner fossil fuels. So the same way coal was phased out, gradually, and oil and gas took the forefront, we can also follow that trend and help the country grow, and the engineering industry in the country as well. So I put up here, a few of the challenges that we have. This is just voice of the customer, what are customers dealing with. I mentioned energy transition. People are worried about, what's going to happen with electricity, electric cars, and the diversification of the energy stream. Then there's also stricter regulations. We've seen, and I'll talk about the Paris, Accord later. But we've seen recently the American president has canceled the construction of several pipelines. They're putting increased in the EU. They're putting increased regulation around oil and gas exploration, and this is driving up the cost. So inspection and maintenance, facilities that are required to run the business are increasing, and so this is sort of driving the business out of business essentially. Now, how does this relate to Nigeria? And I will try to paint a concept. So there's a concept around life cycle assessment, and we're seeing it in the oil and gas service company, where operators, our customers, come to us and they want to know what is the carbon footprint of your operations, not only your operations, but of your equipment. So they're beginning to select equipment and operations based on carbon footprint and the impact on the environment. And it's almost like going to a shop or going to a restaurant to have a meal. Now you start to see how many calories is in each of the meals that you have, and people start to choose based on that. So we're seeing trends where people are more focused on the, the carbon footprint of the operations. And there's talks around how companies and countries in general will start to select their energy sources based on the environmental impact they have on the world. So right now we know that diamonds, for example, diamonds are coded and, so that you know where a diamond is coming from. And if a diamond came from an area where, regulation was not strict, then they wouldn't purchase that. So we can see things going in a way where customers to Nigerian oil and gas business, because we don't use all our oil and gas. We export it. That's where we generate revenue from. Our customers might start to choose where they buy oil and gas from based on the environmental practices and the operations that are going on. So we need to make sure that we're able to develop the industry to a state where it keeps up with the trends. We know that there are certain groups, environmentalists and lobbying for fossil fuels to go away. We need to look at alternatives. What are the alternatives? While those alternatives are being pursued, we need to ensure that we are carrying out our business in the most responsible way. We also need to prioritize opportunities for improvement. So we need to look at areas where we're doing poorly and areas where and focus on those areas and see how we can mitigate those environmental issues. So how are we going to thrive? I've mentioned what the trends are in the business. I've mentioned what the problems are. We know where we want to get to. And we believe that implementing what is being termed generally as Industry 3.0 and Industry 4.0 is what will get us where we want to. So it's a combination of knowledge, technology, and digital capabilities. We know when computers came on board, the speed at which we could process stuff was increased. The ability to work with much larger data has improved. But how do we see that going forward? So this is how it works. And this is how we within the oil and gas industry are looking at it. And we're borrowing from what is being used in the manufacturing industry. So for example, Baker Hughes was part of GE at a point in time, and GE had an aviation sector. Now GE's aviation sector provides or produces jet engines. Because they produce jet engines, they understand how jet engines operate. So they can create a digital twin of that jet engine. So what they're doing is marrying the domain knowledge and the technology, so the hardware, with some data science to understand how it's performing, then how their customers are using those engines, and then they can inform. So we have case studies where they sort of explain to Boeing or explain to a certain airline that if you take off in a certain way, you're able to save fuel. Now that has a direct impact on the cost of running a business, but also has a particular impact on the environment. So here we see, if you combine domain knowledge and technologies, which is what we used to do before, you get the traditional solutions. We know the problem, we know the technology, challenge, technology, bam. Now, in the academic industry, you start to look at domain knowledge and test data, doing some data science, applying, and then, we learn new things, so I say research projects. Now, when you apply data science and technology alone, what you get is ability to find data and to find trends very quickly. Now, the trends that technology, application of data science would have on technology need to be verified. So for example, a typical example with data science is, I'll give an example. There's a trend between, or there was a trend that was discovered between the incidence of burglary and the weather. So they found out that on very, very sunny days, they had incidents of burglary. They also found out that there was a trend between that and the purchase of ice cream. So, what does that mean? It doesn't really make sense. But if you look deep into it, or you speak to somebody who has knowledge, so say, for example, a law enforcement agent, he can tell you that, well, actually, when the weather is better, people go out, they buy ice cream, they're away from their homes. So the incidence of burglary So that is where you need to apply the domain knowledge. And this is what we're really preaching to people who are resisting the application of AI and automation, because people feel that they're being replaced by some machine or something. And that's not what we're trying to do. What we're trying to do is have human or user guided AI. So the AI is just assisting in your processing and your handling of the data, giving you direction. So you look at data and it gives you trends. Then you go and investigate what those trends mean and whether those trends, have any physical principles behind them. So here we start talking about how we apply probabilistic learning machines and machine learning with the physics-based models. So for example, with well modeling, which is traditionally fluid dynamics and hydraulics, looking at flow within a conduit. When you have created a physics-based model around that, using the fluids that you're going to produce, then you can fully understand that you can now apply data science to it so that you're dealing with a large amount of data, say within one well. So for example, you have pressure sensors within that well, sampling every 3 seconds. It's difficult to deal with all that data. You have flow meters that are taking continuous readings. What you would tend to do, and I have done it in the past many times, is find an average. You find an average and work with that, but you are missing the little details which might help you understand exactly what the problem is. So how does this apply particularly to oil and gas upstream? And I'm focusing on upstream for today. I've been speaking with Shenwan and hinting that I might need to come back and give a second talk because this is quite a broad topic. So when it comes to exploration and appraisal, over the years, the whole oil and gas value chain has been shifting their business and their main income streams, but the upstream has been sort of stuck because that is their traditional business. Having said that, upstream is moving into carbon capture and storage, moving into geothermal, moving into blue hydrogen, because we've seen applications of some of our technology into those industries. But the traditional upstream activities need to be improved in order to sustain. We need to continue creating the energy source that's required to develop these other ones. So for example, in the exploration space, companies are now building capabilities to analyze the geological data and, most importantly, the knowledge that is gathered and developed. Now, if you speak to a geophysicist, or speak to 2 geophysicists, they would look at the same seismic data. They would look at the same logs and they will interpret it slightly different, even if they had the same background. They went to the same university, had worked for the same company. It's quite subjective. Now, you need to take that subjectivity and the opinions of these experts and build a system that allows for consistent analysis of the data, so that if you are comparing 2 projects against each other, you know that you've done it with the same tools. Now, they apply data analytics and machine learning to these big data sets that they work with in order to come up with meaningful insights, where to drill, where not to drill, and they need to ensure that they have repeatable success. Now, moving down the project life cycle, if we look at concept development, where you have a number of opportunities and projects that you can go after, and we can call this project evaluation or development and planning. Companies are changing the way they choose the best projects that they go for by combining more of the data and the parameters. So typically, if we're doing a risk or risk analysis for a project, we would like to choose key parameters, key considerations. Right now, with data analytics, you can choose all possible parameters, and then allow the data to filter out, allow the machine learning or the advanced analytics to filter out the ones that are not required, the ones that don't show any correlation, the ones that have no bearing on your decision. So that is what we are able to do with the project in project concept space. So we first start with digital modeling, model the different parts. Then you start to build digital twins. Now, the most difficult part of the oil and gas industry is building a digital twin of the subsurface. It's the part of the ecosystem that we didn't build. It's the part that we would probably never fully understand. So we need to take a probabilistic approach to that. And then you compare different concepts in terms of how to develop the field. You run different scenarios of different development scenarios, different cost scenarios, different production operation scenarios in order to find out the one that's got the best outcome for you. Now, typically you'd be working with, in Nigeria, DPR, which would have a much longer term interest in the work and would now be looking at the environmental impact and the sustainability of your operations. So finally, in the drilling and completion stage, we start looking at drilling solutions that help identify risk and manage this risk. So drilling hazard mitigation. One other thing that is quite key is reducing the number of personnel on site. So very recently in China, there was a fire on a rig, and a few people were hurt, and I think they still have a few people that are unaccounted for. What we would like to do is have less people on the rig site. I remember when I used to go to the rig, we used to be packed. We used to be at least about 90 on the rig. Right now, they're able to apply blockchain technology to allow the different service providers share sensitive data in one common ecosystem, and that fosters collaboration. Now, with collaboration and transparency, there's also the reduction in cost, there is the ease in decision making, and in turn, there's the management of resources. So we end up with a more efficient system that reduces the impact in terms of cost and environmental impact. Now, in the production space, which is where I'm going to focus on for most of the rest of the presentation, we start looking at things like predictive maintenance, performance monitoring, and operational excellence. With operational excellence, we're talking about how you can simplify your operations while ensuring that you have minimum disruption. Now, when I say disruption, I know I'm speaking about digital and AI and how disruptive it is. But when I say disruption to operations, I'm talking about downtime, non-productive time. And then how with remote surveillance, you can monitor your performance, so you have a single, visible view of the entire ecosystem. So to production operations, as I promised, this is how we sort of operate in the industry at the moment. So different aspects of the company managing different databases in different formats, and everyone's really managing their own KPI. The drillers want to drill and complete a well, how quick they drill that well, and how easy, and whether they come out of hole. That's what they're managing. The facility manager wants to ensure the integrity of his facility, and the production manager wants to ensure that he's delivering the promises that he's made. But that is not an efficient way of working. So what is being trialed in a lot of companies at the moment is applying Industry 4.0 to all these aspects to bring them together. So we continue to see companies connecting pieces of their operations, the little pieces that they have been sort of digitizing and analyzing on its own. They're now starting to manage all those ones in terms of cost, in terms of performance, in terms of damage or downtime, and the environmental emissions. So gas flaring, CO2, power usage, all that is beginning to be analyzed. But what is being proposed is that you stitch all those little pieces together. So all the databases come together into one unified data image. And the whole application is based around collecting the data and ingesting and digesting large amounts of data. So in the industry, we have all this Industry of Things sensors and remote control drones that can gather data, surveil individual assets in real time. All that technology has been around for a while. It's now being applied into our everyday life. So we're talking about how Amazon wants to deliver with drones. We've had drones in the system, oil and gas system, doing monitoring for emissions or for security in some cases. So the first thing we need to do is aggregate all that data that comes in from different sources, because it's in different formats historically, because it's been developed for different applications outside the oil and gas. Then we struggle. So first of all, we apply data analytics and artificial intelligence techniques to evaluate the productivity of each of the individual assets. And then we start to predict the performance and maintenance schedules that are required to operate functionally. Then, we start to make decisions based on that. And I'll turn to the graphic here. So the first thing to do is sort of create a data lake, what we like to call a data lake. You put all the data together in such a form that every piece of the puzzle is hosted in a particular place. Now, the next thing is for us to find the physics-based models for each of the individual components of the system. So, for example, for the wells, you have a well model. For the facility, for the flow lines, you have a gathering system. You sort of model that on its own. For compressors, if you had compressors, for power generation, power utilization, all that is modeled separately, typically. What you need to do is pull that into an integrated system. So you have an integrated production model that is very, very complicated, but captures the interdependencies of each of the components. So we're looking at, not the small details. We're not treating the symptoms. We're not treating the individual KPIs of each of the stakeholders, but we're looking at the whole picture, and we're not missing out on the real problem. Now, with the integrated model setup, you can now apply data analytics and machine learning to what experts would typically do. So, we have machine learning on our phone. We have predictive texting because the computer is constantly learning from you. It's the same way you start to have machine learning. So the machine starts to learn that based on these actions that are inputted into the system, the outcomes are more likely. And so the next time you're going to choose, or you're going to prescribe a solution, then it gives you the probability of success. It starts to tell you which of the products you should apply and which products you shouldn't apply. And then all this is pulled together in a single visualization platform, which we like to call a single version of the truth, because you're seeing everything. With increased visibility, you can manage your assets better. So when all that's together, so we have the integrated model, we have the visualization platform and the data analytics, it's not going to work on its own. It's not going to do all the work on its own. You need to have the users and you need to have the automated technology in place. Now, with different systems, you have either autonomous or semi-autonomous controls on the systems, which I will get into in a bit of in a few slides down. And with all this, we're able to improve the efficiency. So we're looking at reducing interventions. When a well has a trouble, you have to go into the well, you have to mobilize, and that has a cost to the operations. We're also able to assure flow, so ensure that you have less failures by applying chemical treatments or proactive maintenance or changing the way you operate your system. With this also, you have increased recovery because you are producing your field in a more responsible, a more optimal way. Then you can increase the field's economic life. And you can also reduce the OPEX. So when you reduce the operating expenditure, then you stay in business for much longer. And then, the final thing is reducing the carbon footprint. So an example of how we can reduce carbon footprint with this is with, for example, tank monitoring. So we pump a lot of chemicals into our wells and into our fluid streams to ensure that we are beating corrosion or that we are reducing the drag forces in the system and the pressure losses. We have a lot of people having to drive to the sites to check tank levels, to check that things are working when they start to see changes in the readings at the flow station or at the office. So you can imagine the amount of logistics around driving to some of these really remote places to ensure, even back in the days, and I'm hoping that things have changed, you literally had to drive to the wellhead to look at an analog gauge on top of the well and to take a data reading for that well for that particular day. With this smart technology that is even being, incorporated into edge devices and, it's going into the cloud right now, you can reduce that. Now, more importantly, you can reduce the exposure. So it's not much the cost, but the exposure of those human beings to, road traffic accidents, to the chemicals that they're having to deal with. So the topic is quite broad, and I'll focus on reliability of one of our popular downhole rotating equipment, which is an ESP. So what is an ESP? An ESP, electrical submersible pump, is a series of multi-stage centrifugal pumps that are operating in a vertical position. So what you have is you have the impellers and you have the rotor, and you are creating a head as these this rotates. And what the head does is adds pressure to the system. So it's a vertical lift, vertical lift assistance system, and we employ it for many reasons, either because the reservoir pressure is too low, or the fluids that we're pumping are too heavy, or just to boost the production because we want more production, or to reduce settling of solids. And here's sort of like a typical performance chart for that. So here you have the head that you create, you have the efficiency, you have the power, and you come up with an operating window that you should operate the well within. Now, this is design conditions, but what happens in the field is that the wells start to produce at a higher rate. Over time, the rates reduce, the fluid stream changes, you start producing more gas or more water or less oil, and you start to stray outside the operating window. But how do you know that if you're not monitoring the performance of the machine? Now, within this machine, as you can expect, it's a rotating equipment with fluid passing through. So if you're producing sand, you start to have erosion of your bearing. Erosion of the bearing will cause a bit of vibration because you have misalignment. So if you had sensors on there, you can pick up the vibration. You can understand that your bearings are weak. If you had temperature gauges there, you can understand that the motor that drives this, because as you can expect, there's a motor, the motor is down here. So what we do is we allow the fluid flow past the motor and expect that the fluid will carry some of the heat from that motor away before it gets into the pump. Now, if your motor is heating up, you need to be able to know that. You need to be able to adjust the frequency of your operations at which you're operating the pump in order to avoid failure. Now, where failure cannot be avoided, then you need to plan for that failure, either by proactively pulling the equipment out of the well or doing something, something different. Now, one major problem with ESPs that we've seen is plugging of the inlet. So the inlet to the pump can be plugged by sand. In some cases, plugged by scale. Now, you recall that I mentioned that ESPs are applied when you're producing heavier fluids. These heavier fluids are typically water in the Niger Delta. So in the Niger Delta, we are blessed with lighter oil that flows quite well. But when you start to produce water, then the fluid stream is heavier. So that's when we employ this. Now, that same water, while it has one particular benefit of having a higher heat capacity and being able to dissipate the heat from the pump quicker, it also creates scaling and corrosion. So you start to have two problems that can affect the reliability of the pump. And every time these pumps go down, you have to wait a number of days to go in and fix the pump. So how can we apply AI to rotating equipment? So we've had a lot of improvements in the past, focused around increasing productivity, production optimization, where we run the pumps at a by looking at the leading indicators for pump performance from that curve, and sort of modeling the pump to the nth degree, we can see that approaching this particular limit will cause failure. Going below this will cause down thrust. So you stay in the sweet spot, and you ensure that even if you're not producing maximum production, but you're producing optimal production over a period of time. And then we started to move into, within the industry, started to move into decreasing costs, because again, it's driven by profitability and the stakeholders. So condition monitoring, which I've been talking about, preventive failure diagnostics, maintenance scheduling, inventory management. A lot of these companies have to hold a number of these pumps in their yards just to ensure that they have pumps to swap out. Now that can be a huge cost if you're having to deal with that. And then managing the resources. So again, it's an electrical submersible pump, so you're dealing with power consumption. Within Nigeria, within the Nigerian oil and gas industry, that power is typically generated at the well site or on the flow, or on the upstream operations. Whereas in some other places, you might have to buy power from the grid. So within the Nigerian oil and gas sector, we haven't really advanced into utilization. The gas that's produced is used to generate the power. So it's almost like the power is for free, but it's something that we need to go and have a look at, because going forward, gas might as well be the new oil, and then gas becomes really, we sort of get a handle on monetization of gas. Managing resources, where do we want to deploy our resources? There are always a finite amount of resources in terms of rigs, in terms of personnel, in terms of money. So we need to ensure that now system redesign, every time these pumps are pulled out of the well, there's a new one that's running. Now it doesn't make sense. I mean, you've all heard, doing the same thing over and over again and expecting different results is just not smart. So we need to constantly understand the failure mechanism for the pumps in particular, and how we can redesign the pumps to ensure that the run life of these pumps is increased. So all that's going to increase your profitability and your capital efficiency, in the same ways that we've been that I have been speaking about. Now to go into some of the detail, it's been a bit difficult for me to present this part without actually using the tools that I need. But unfortunately, the tools that I need are proprietary to Baker Hughes, and some of them are third party, but purchased by my company. So I was unable to get permission to do that. So I've sort of tried to build a story around some test data that we've sort of worked with in the past while developing some of these workflows. So here, what we're looking at is the survival analysis, and it's just, population of ESP run life for a certain asset. And the steeper the curve is, the less, you end up with a shorter life cycle for your pumps. So these pumps, and this is a group of pumps, these pumps are doing much better than these pumps. And with data analytics, you can throw in all the data from 100, 200, in North America, you're dealing with 1,000 pumps at once, and do failure probability. Now, what it starts to show you trends between types of pumps or when they were installed. If you're working with multiple vendors, it might show you what, installation date, it might show you the models that were used, and then you start to group that. But that is just the beginning of understanding the mean time to failure and how the different things around, the ESP run life affect it. You now need to match this data and these trends that you're seeing to other parameters to get the full picture of why your wells are failing earlier than, or how you can improve the reliability of these pumps. So you match it with data like, equipment design, the type of pumps, the design limits, the conditions in which you're producing these pumps, chemical treatment, what sort of chemicals are you putting in? What sort of chemical programs do you have? Batch treatment, are you just pumping in corrosion inhibitors, or scale treatments intermittently, or you're constantly dosing the fluid stream with it. What's the concentration that you're using? What's the dosage? Where are you injecting that? All that, those are key parameters that you can throw in to the mix to start to understand how much water are you producing? What type of fluids have you done some analysis of the fluid chemistry to see whether it has tendencies for precipitate, tendencies for scaling, tendencies for whether it's got CO2 or H2S, which are, corrosive in their at their individual partial pressures. Then what sort of sensor technology do you have there? Because the sensor technology you have there gives you the ability to monitor. So that starts to, play a part in how much you know about your operations, your current operations. And then how are you operating these wells? What's the installation procedure? Are you putting these wells on production right after installing? Who is doing the installation? What are the control mechanisms? So with ESPs, typically you'd have a variable speed drive, which can change the frequency of the pump to manage the speed. In some cases, you don't have a VSD, variable speed drive, so it's an on and off switch. Now, you can imagine the torque that would be applied to a well that's got some fluids above the pump. So the pump is starting. It's almost like when I was much younger, I said, don't start your car with the AC on. I don't know why, because right now we start the car with the AC on. But that was the thing. Don't start the car with the AC on because you're giving the car a bit more work to do. So you have a head of fluid sitting above your pump and you start it at maximum or set frequency that can snap the shaft, that can wear the bearing. So you need to understand how those wells are controlled at surface. So I'll give a good example, and I've tried to sort of populate some data from one of our test cases. And what we see here is the dosage of the chemical, and in this case, we're looking at corrosion. Corrosion is a problem here. The dosage over time, and trying to marry that with the incidence of failure. So here we see so HIT is hole in tubing. So sometimes it's not the pump that fails, it's corrosion to the tubing, which is the pipe, the conduit, that causes a failure in the system, and then you have to pull. So we're treating the pump metallurgy, and we're also trying to treat the pipe metallurgy as well. So here we can see there's an incidence of a spike of hole in tubing, but generally you'd wonder what happened here. The problem didn't start to happen here, and we'll see that later. It started to happen much earlier, but looking at this on its own, which is probably what the production engineer himself would look at, is saying that, okay, well, maybe the problem started sort of like here when we're, or maybe it's because we have a low ppm that we're having this spike, but the problem started much earlier. So if we start to look at things like number of installs, the number of pulls, we start to look at things like, this is batch. Here we have batch inhibition for corrosion. We're talking about corrosion inhibition. We're looking at batch inhibition. What is the target? What is the prescribed, So we've done some modeling to say we're going to deal with this type of fluids. This is how much you should produce, and this is how much you should inject. Now, where you have manual injection or not fully automated injection, you would have some ups and downs based on either tank level monitoring issues or power to the pumps. So you tend to have a bit of fluctuation, but where you are consistently below your target for this long, then you start to create an issue. Also, we group the wells in such a way that we're looking at continuous corrosion inhibitors, the ones that had surface pumps that were constantly flushing the system. And we can see that within that particular period, you have a reduction in the use of chemicals. It turns out this is sort of learning from when this was presented. It turns out that the chemical dosage was reduced to save cost, but the implication was not seen until much later. So you start to see that, your tubing pulls are increased over time. Then we start to look at the ESP types for the wells that failed. You know, why are some wells failing? Why are some wells, you know, much better than the others? And you sort of start to add all the pieces of the puzzle together. Then the next thing you start to look at is failure mechanism based on either continuous monitoring and continuous treatment or batch treatment. Now, all this is done in software that has algorithms, you know, written to ensure that we can handle the amount of data that we can. We can filter out the data that we, you know, the outliers, and ensure that we're dealing with, you know, not the pumps that for some reason there was a grounding issue. So in this analysis, we've taken out the issue of power failure. So it's only related to corrosion, because I'm talking about corrosion, chemical treatments, and its impact on the pump life. So by piecing together, and I'll go back to here, by piecing together all these different parameters, and we can, you know, this list of parameters is not exhaustive. Anything that we think that can have a bearing, even just thinking, you know, so you sit down in a room, you frame the project, anything you think can have an impact, and you are able to collect data on it, you can throw it into the mix and then start to analyze the data and see, you know, the trends that are developed and how these trends interact with themselves. So what are the key benefits for this? You know, first of all, in production operations, we can start to enjoy system debottlenecking. So again, I speak about an integrated production model, integrated production model that looks at reliability of fixed assets. So when I say fixed assets, I'm talking about pipelines, flow lines, wellheads, you know, separators, and then rotating equipment as well. We also start to look at utilization of resources. So power, water in some cases when you're doing water injection for pressure maintenance or for reservoir flooding to mobilize the fluids towards a particular well. Everything comes at the cost. So the cost of burning that gas rather than selling it, the cost of purchasing power or the cost of generating power using the gas, the cost of sourcing the water and treating it, you know, that has an implication. You know, then we start talking about consumables. Now, one part I didn't mention in the previous analysis was we started to look at the optimal dosage. So the fluid chemistry will change over time. If you are able to carry out sampling, and we now have digital systems that can actually read off hard copy reports. So with certain customers, particularly in Central and Southern and East Africa, you have systems that are still quite analog. So people are still, you know, going out in the field and typing out an Excel. Now you need to digitalize all that, and in such a way that your system can read off a report and incorporate that data into the system. So we start to look at chemical usage, how much, you know, chemical, what's optimal usage of chemical in order to reduce the cost again. Now, asset reliability is one that has two angles, reliability and integrity, because with every damage, there is, and I mentioned it before, there is a carbon footprint implication in relation to resolving the problem. And in some cases, it might have to do with the spills and dealing with that particular problem. So how do we minimize downtime and increase the production? How do we protect the environment, ensuring that, you know, corrosion is avoided? How do we stop scaling, which will deposit in the system and would need another activity or a different chemical? And some of these things might even just be related to the way you operate. So scale, for example, will drop out of a fluid stream based on temperature and pressure. So if you're operating your well at a certain temperature or pressure, you can avoid scaling. Now, and where scaling cannot be avoided, it's better to treat that scaling, better to have an inhibitor or, you know, something that ensures that the scale is suspended within the fluid stream and does not hinder that. And then we can also start to set safety standards. Maintenance and inspection, and you will not believe this, maintenance and inspection accounts for at least 30% of the cost of lifting 1 barrel of oil in most parts of the world. So again, if I remember, I think security outweighs that in the Nigerian sector, but again, that's a peculiarity. But the amount of maintenance and inspection that has to occur, to check the pipelines, even if it's as rudimental as somebody driving down the pipeline with a certain probe or some monitor to check pipe thickness, all that has a huge cost. Now, with AI and sensor technology, you could have non-destructive, non-intrusive systems that look at your integrity. And over time, you can then start to predict the integrity, degradation of your system and come up with a more optimal schedule for your maintenance and inspection. Maintenance and inspection is not going to go away. It's in most parts of the world, it's a requirement by the regulators. People tend to do it more than they need to avoid, because of the uncertainty around the integrity of the system, to avoid any damage or any catastrophe. And then production assurance. When we talk about production assurances, flow assurance, ensuring that the asset is fully utilized, ensuring that the system is optimized, ensuring that you have minimal obstruction to your process. So with oil and gas production, once you have water mixing with oil and gas, which it happens a lot of times, you might have stable emulsions, which will then form within the system, prevent separation. Your separation now becomes less efficient. You start to have carryover of oil or water into one of the pipes, and then it sort of reduces the price that is paid for that, because somebody has to deal with that water. Heat might have to be introduced to reduce or to remove the water. So all that, and essentially having that visibility, having a system that can detect failure, having a system that can, give you alarms that let you know when the system is going out of the design or desired specification, and treat that as soon as possible. So where are we within, in the Nigerian industry? And so I've sort of pulled this out and tried to map out where I think we are. So on the x-axis, you have the development path. So this is sort of like a typical digital transformation journey. And on the principal y-axis, you have maturity, and then you have business value. So value increases going this way, and maturity as well. So in Nigeria, we're already applied computerization. Connectivity is there. There's permanent downhole gauges with surface readouts to the office, via SCADA systems. That's all in place. So what can we do with that? We can collect the data. In some cases, we can see what's happening and we know what's happening. But without a full understanding, without moving into this visibility, transparency, predictability, we're losing out on a lot that we can be doing. And with that, it sort of relates back to what I was saying about the energy transition and how we view the oil and gas business going forward, where we would need to be a bit more responsible in the way we get hydrocarbons to our customers. So we now need to start looking at how we can improve visibility, how everyone can be looking at the same data, everyone can see the big picture. And the question most of my customers ask me, say, if it's so easy, why aren't we doing it? I say, because the key piece is managing the data. Now, outside the oil and gas industry, and probably outside the typical traditional engineering domain, we don't like to view things like a black box. Now, if someone's coming from outside the industry and is bringing a system that's going to do X, Y, Z, we want to understand it. And so we've taken a bit of time to understand how these things work, because we don't want to be landed with a black box that we don't know how it operates. We don't know how we can we don't understand how we can interpret the insights that it's providing to us. So having full visibility, knowing what's happening where, having transparency to understand why this is happening. So we're not relying on the provider, the service provider. Now, I work for a service provider that provides pumps I might be working in partnership with a competitor who's providing, say, for example, the cables to the pump, and then a third provider providing the chemicals. Without the customer having transparency of the data that's related to the operations of, the pump within the oil well, you start to have, say, provider A saying the pump isn't the problem, it's the power. Provider B saying, no, it's not the power. The power cables are being eaten up by corrosive fluids. So the chemical injection is not working. But with transparency, you sort of start to understand exactly what's happening, how this is affecting this, and it fosters collaboration. So then we now start to, go into predictability. What do we need to do? We understand what the problem is. We understand why it's happening. We understand where it is happening. So where the risk is highest, and what can we do? And then we sort of move into semi-autonomous systems. So for example, with the ESPs, we are able to see leading indicators to performance. And based on those leading indicators, we have edge devices that can kick in and create and create a command to the system. So for example, if you see a rise in vibration within an ESP due to wear in a well that you are producing solids, you can have the system speed up the production or speed up the pump for a short period in order to get rid of all the solids within the system, because solids will have clogged. So again, we're dealing with solid transport. There's a threshold at which the solid starts to deposit within the well. There's a threshold at which it starts to deposit within the flow paths of the pump. Now, getting those out of the bearing and out of the pump might require, to speed up the pump for a short period. So to flush the system, and those things, they don't have to be activated by personnel. They're guided by personnel, but they're sort of semi-autonomous, just like our flow distribution is. And then we go into adaptability. So that's what I'm talking about, where you start to have this, self-optimizing systems that can start to ensure that we protect the capital investment that we've had in the system, in the field. So how can we develop this for our industry? And I'm talking about in Nigeria in particular. What sort of skill sets, what sort of frame of mind, what do we need to get our engineers? What do we also need to, again, what do we need to start to teach our students in the university, those who are going to replace us in the industry, to do? It all comes, around understanding what the problem is, building a solution, the perfect solution, and then operating or executing flawlessly with speed and with perfection. So first thing we do, and this is just a work stream that we've developed to work with some of our customers. First thing we do is we have a customer workshop where we sort of frame the issue, get all the data together, where we understand what the customer's challenges are. In most cases, the challenges are usually symptoms. Oh, my wells are going down that's not the challenge. The challenge is you're dealing with corrosion, but what they see is the symptoms. And if the customer doesn't understand what the challenge is, then we sit down with the customer, we look at the data, we apply some, very, very basic data science and start to probe further. And then once you agree on the KPIs and things that you want to resolve, because it's a journey, as I mentioned, it's a digital transformation journey. You can't go from just from computerization to adaptability straight away. You need to, test things out, have a proof of concept project, test this out, make sure it works, go to the next level and go to the next level. So once your target KPIs or, deliverables have been developed or have been identified, then we go into the solution development phase, where we start to look at the subsurface, because everything, again, I think Emmanuel mentioned it in my intro, everything is reservoir driven, reservoir centric. The reservoir provides the fluids, the type of the fluids. The reservoir drives the production of the fluids or the flow of the fluids into the well. Reservoir also introduces some unwanted fluids and some solids as well. The temperature aspect is there as well. So we now need to start to analyze what, the data from the reservoir, from the subsurface, to establish the critical digital tools that we need. So we start to make recommendations on sensors, where the sensors should be, what sort of sensors you need to have. We start to customize the user interface. So we now need to, the customer wants to be able to see X, Y, Z. He wants, a VP of production, for example, wants to be able to see pipeline integrity, assets utilization, and production forecast. So you need to customize that interface for the customer. You need to identify the key production technologies that you want to use, whether it's intervention or whether it's reduction of intervention or it's production enhancement or flow assurance. We need to do that. And then you now need to deploy the complementary digital tools that will transfer the data that's been collected by the sensors into this integrated model that we've been talking about. And as I mentioned before, you then need to have, implementation. So you have to have the automation and control systems in place. And so it's typically like a gated process. So at every point in time, a decision needs to be made, whether to proceed or not, whether to rationalize. Again, there's always opportunity costs. So our customers would always rationalize what they need to implement based on their priorities. So that brings us to my last slide, and then we'll go into discussion. So just a brief recap. I've focused on implementation of ESP management today in the corrosion space, but practically all aspects of our oil and gas production operation system can have a similar work stream that's centered around, the traditional oil field service technology with data science, data analytics, machine learning, and then the domain knowledge. Domain knowledge is in two parts. So it's the subsurface domain knowledge and also the technology application knowledge as well. So you need to have ESP experts, people that understand. So the most obvious one is, is the ESP, because it's one part of the well operations that is most likely to fail. It's it's one of two rotating pieces in the fluid stream. So how do we evaluate the risk? We analyze the data that's available, the large amount of data that's available. We develop trends between parameters. Those trends are verified by domain experts to understand whether those trends are really are real, or whether they're just artifacts within the system. And then we now develop solutions to resolve the problems that we've already identified. These solutions could be also traditional technology, so applying chemicals, applying flow control, changing our operations, and the technology that we apply now needs to be automated and controlled to ensure that we remove the human error, we remove the risk associated with monitoring physically, the logistics that is related to that, in order to ensure that we have flawless execution. Now, why is that important? It's important because we're going through an energy transition phase where cleaner energy is being favored, and we see a need for us to be as responsible as possible to ensure that we are perhaps not able to match the cleanliness of the fluids, of the energy that we're producing, but we're able to bridge that divide between, production of oil and gas, which might be generating X amount of CO2, and geothermal, which is doing, X minus 10. We try to bridge that gap in order to ensure that the Nigerian oil and gas industry sustained for much longer. We know that there is a shift away from oil and gas into other renewables, but we also understand that there's energy required to generate or build the infrastructure that supports those other new renewable energies. So we want to be part of it. We want to ensure that our oil and gas is still marketable in the international market, is still favored in the international market, and we're not left with a resource that is now, for lack of a better word, almost worthless. So I would like to thank everyone for this very, very brief discussion. Again, I would like to appeal to Dr. Sheon, as we like to call him, for a second chance to come and perhaps demo some of the analytics we do, and maybe expand into another part of the business, and hopefully inspire some research work and some focus on how we can help our industry survive. And with that, I would open up the floor for questions.
I'll just jump in here to first appreciate you greatly for this talk before the questions. I think this is superb. This is world-class level presentation and details given here. This is what countries like Nigeria should pay for, to hear from a global lead and global expert. Thank you so much, Ayo, for doing justice to this topic. The comments in the chat box already says it all. Someone said the lecture is so loaded. We have RCM, that's reliability, maintenance and maintenance standards, automation and control. All of these elements carved into the Industry 4.0, the big data, self-optimizing systems and value-based discussions. Someone's mentioned that this should be available for postgraduate and final year students, and I thought about that as well. So the video of this is being recorded and it will be uploaded on our YouTube page. We have the permission of the speaker for that. So you can direct people to see it. I'll share the link to our YouTube page at the end of this program. So stay tuned for that. Someone's also said, I like the underlying statement. I also understand that energy would be required for the renewable energy infrastructure. Yeah, and so many great comments coming in. I think there's going to be great discussion, so I wouldn't take too much time. I just wanted to appreciate you once again for this wonderful talk. I'll be handing over to my colleague, Engineer Sharp, who will be coordinating the questions and answer session and the discussion with you, Ayo. Thank you so much, Ayo. Engineer Sharp, over to you.
Thank you very much once again, to lend my voice to the appreciation to the speaker. You've done an excellent job. So as we go into the question and answer session, please, there are two ways we will recommend. One is if you could type your question in the chat room, and you would your question will be read, and then the speaker will attend to that, attempt to answer the question. Or the second alternative is the file. You could raise your hand electronically. I know we quite some people, a number of people here, so we might not be able to go face it. Some people are not on camera, so there's a way you can raise your hand electronically from the chat side of things. So if you raise your hand, and then I'll get to call you out to verbally present your question. But please, let's keep it short and straightforward so that others can get a time to fill in their own questions. So I'm yet to see it.
Yeah, just before the questions start flowing in, I'm sure people will start pouring in the questions very shortly. Just want to mention again, as the chairman said in his remarks, that we have important dignitaries here, lots of important dignitaries, but I just want to single out two dignitaries who will be speaking to us after the question and answer session. So just keep bringing your questions in. Just want to mention that we have with us the past president of the Nigerian Society of Engineers, Engineer Ademola Isaac Olorunfemi, FNSC, FNIM. He was president 2014 to 2015. He's with us and we'll be talking briefly after the question and answer session. We also have Engineer Professor Olusoji Ofi, the father, I think, of the speaker for today. He was Deputy Vice Chancellor.
Then email us. You have some sort of genuine reason why. Email us.
Right, if you can keep yourselves mute, that would be appreciated. Thank you. So I was saying Engineer Professor Ofi was a DVC, Deputy Vice Chancellor Admin, University of Ibadan in the mid-90s. And he's a patent holder for the popular Poundo that we all know about. And he's also present, and he will be speaking to us right after the question and answer session. So I'll hand over to Engineer Sharp again. I think the questions are coming in now. Over to you.
Thank you very much. Okay, so just to reiterate, if you can raise your hand and then you could present your verbal question, or you could type it in the chat room, and then we get to read it out. I think I'll just go for the few questions that are in there at the moment, or a few comments. If you want to also make an observation or some kind of view, if you could keep it short, that will also be welcome. So we could take your point if it's not necessarily a question. I know we are pressed for time. So let's see what we have here. Okay. Sorry about that. I'm trying to get the questions that are in the room.
Yeah, just to mention that the video will be available on YouTube. So the whole talk will be uploaded to our YouTube channel. I'll share the link at the end of the program. So for those asking if the presentation can be sent to them, you can access it on the video on YouTube. So that will be fine.
Okay. Right. The first question I will read out here is, speaker, what is the software you use in the analysis and how is it different from Eclipse? So my brother Ayo, what is the software you use in the analysis and how is it different from Eclipse? So that was the first question, if you know that, and then we can take the second question.
Okay, so I'll answer. So Eclipse is a reservoir modeling package by Schlumberger, which is a numeric simulator for flow and pressure. So that analysis, that software package was not used for the failure analysis. We used a proprietary physics-based model that's been coupled with, we're in partnership with a company called C3AI. C3AI are leaders in the AI and machine learning space. And so we've coupled one of our physics-based models, which is called Autograph PC. Autograph PC is a well modeling tool. So it's fluid hydraulics, particularly related to artificial lift types. So everything from rod lifts to PCPs to ESPs and gas lift. So it's a different package from Eclipse. Now it's proprietary to Baker Hughes, but there are also other packages like that. Petroleum Experts, which is based out in Edinburgh, has a Petroleum Expert suite. One of their packages is called Prosper. Prosper can be used for well modeling as well. It has artificial lift capabilities. And there's also, I think the Schlumberger one is called Well Flow as well. But the truth of the matter is there are a lot of other free packages out there. They're not as robust. Some of them have been developed in, free of charge. Some of them have been developed in Excel. You'd be amazed what people can do with Excel. That just basically model the pump and can now carry out prediction. Well, why we use our package is because we have a flow loop in Rankin Road in Houston, where we've actually tested the performance of this. So we've calibrated our own software to several pump types. So we've gone through the extra testing to ensure that the calculations that have been that's spitting out are accurate as possible. And we continue to update that. So the software we use is the base software. What's under the hood, under the bonnet, is called Autograph PC. And it's a well modeling package designed particularly for artificial lift systems.
Okay, thank you, sir. Right, has any comprehensive, that's the second question from Engineer Ibrahim. Engineer M.O. Ibrahim is asking, has any comprehensive Internet of Things been deployed or developed for any real project based on your presentation? So talking about AI, integrating it with Internet of Things. So please respond to that.
Yeah, we have a few products out there, and I try to stay away from, being seen as branding or, pushing my company product. But we have a few products, edge devices, with Internet of Things sensors that operate within that pump reliability and fluid chemistry space. The difficult part of the business where we're sort of looking at development is sampling, fluid sampling, without obstructing the flow. So we're working on a number of non-destructive sensor technology that allows us to understand the fluids, looking at it from outside the pipe. So looking at some of the ionic reactions between, or interactions between the fluid and the pipe to make inference. It's the same technology that we use in cased hole logging. So when we're logging wells to understand where the hydrocarbons are, where the fluid behind the pipe or the fluid in the field, in the reservoir, the tools send out some radiation and then we monitor how that comes back. But because we're dealing with this at surface, we're trying to reduce, which is why I talk about non-destructive. So we're trying to step away from radiation sources. And so we're using similar technology, but that was where it was born from. So we have a few edge devices like that, mainly around understanding the fluid chemistry, continuous sampling, where it's quite critical. I would stress that at this point, the technology is a bit expensive, so it's only applied where the benefit outweighs the cost. So in certain places where an example is working in a nature reserve in the middle of Italy, which is operated by an operator, and so sensitivity around carrying out sources, sensitivity around logistics is quite key. So we ensure that we sort of deploy that sort of technology there.
Okay, thank you. Thank you. I guess the next question is going to be not just to you, Ofi. It's also going to go to the chairman of the branch. He will comment on that question. Can the chapter, that is this NSC chapter, link up with academics as adjunct staff, so that adjunct staff, so that theory can be matched with practice, to make it a very concrete learning experience for the students. So for the presenter today, I mean, this is a question to the branch. The chairman of the branch will need to comment on this, if not now, later on. So if Becca Hughes or yourself, or if you are in a link with any institutions or where you're delivering kind of partnership lecture, so maybe you can comment on that, and then the chairman can answer later.
Yeah,
I'm not at the moment.
I'll just to step in cover for engineer. So what's happening is, we as a branch, this is the whole essence of organizing this kind of webinar. What we are looking at with the institutions. One of the problems we have in Nigeria, and is the key problem, is there's so much stuff in and the actual practical. And what we are doing as a branch is to how we can bring things together. At the moment, we are going through a process whereby different investors have been coming to us, and we are working on a process of partnership with them. We are focusing on Nigeria, and also definitely a lot of universities in the UK, they are partnered with us by the fact that a lot of our members and our executive, they are, whether they are lecturers or they are, researcher in those universities. So the answer to that question is, if there is any of people that, the person that is asking the question, if you're interested in, that sort of partnership, we are more than happy to create that link between that institution and engineer. You can always come in and give his support later on, depending on the time. So we are more than happy to, to create that. And we are doing that already just now. Not just for this topic, we are doing it, and you start seeing that reflection just now. But if you want to step in just now, please send us an email through our contact at the nscglasgow.org.uk. Then we'll be able to, key into you and respond to you appropriately. Thank you.
Yeah, and I just wanted to add that with the pandemic and the issues we're having at the moment, and schools adopting sort of like virtual learning, it would definitely make things easier to reach out to many more universities and have this sort of talks that we're having. With the incidence of using Zoom and all this, we can sort of arrange this. And I'm sure my father, who at some point in time hoped I'll become a professor, will be very happy for me to do that.
Okay. Thank you very much for the two answers that come in. Now, that more directly to you, Ayo, is can we use AI to monitor capping? If so, if we can use AI to monitor capping, how? That's a question.
So by capping, what do you mean? It's not a term that I'm too familiar with.
Okay, I will.
Oh,
I don't
gas
want
capping.
to
Okay,
engage.
he's answered. Dr. Adiaga has answered. Yes, yes. So one of the applications we have is relating to production of, so gas capping, as I am interpreting it, is the production of a secondary gas cap when you reduce the pressure within the system and your gas starts to evolve within the reservoir. So you now get gas trapped in the reservoir. What that does is it also pushes down the gas oil contact and produces gas in a zone that didn't have gas before, and so you reduce the recovery from that. Now you need to manage your reservoir production, your reservoir pressure, you need to manage your rates. Now with AI, you can easily calculate that critical velocity that will mobilize the gas, because if the gas is produced, if inevitably you're producing below your bubble point, which is the pressure at which your gas starts to evolve, if the gas is produced, but you're producing the fluids at such a speed that you've reached critical velocity to mobilize that gas out of the or through the pore throats, then you can prevent gas capping. Another way of preventing gas capping is by introduction of water to fill the void. And then finally, there's a system that we have. It's a bit of an unconventional system that was developed for a particular customer that was having a gas cap production, gas cusping problem. So they were producing oil, very, very light oil, in a thin oil rim. So I think it was about 100 feet thickness. And with minimal production of oil, they were having gas coming in. It was affecting the production and choke, because gas is more mobile than oil. So what we did for them was we actually did 2 completions, and we had to run different scenarios. Again, using reservoir simulation and some, integrated models, quite basic models. But the engine behind the scenario, which was controlling the different scenarios and different options, different runs we were making, was actually AI based. This was 2016, so it's still quite, new AI to my group at that time. So we controlled the scenarios and the runs to understand the best situation. What we found out was that the best way to prevent that gas from flowing into the wells was by producing that gas at the same time. So typically, operators will go in and produce the oil first and then produce the gas, or produce the gas first. And actually, produce the oil first, then produce the gas, because you don't want the oil to move into the gas zone and you lose some of the saturation in there. But what we found out was that you needed to produce the oil and the gas at the same time. So these wells were then completed with dual tubing. One landed very shallow in the gas cap to create a pressure sink in that gas cap and to prevent the gas from moving into the oil leg, where you're also creating a sink. And that was a very simple solution. So in most cases, you look at the problem and you apply AI and data science to analyzing the problem, apply it to developing the solution, and you can also apply it to implementing the solution. So how quickly or how much gas you're going to produce to balance that pressure sink in the oil leg and in the gas leg, again, needs some further analysis and needs some continuous further analysis. So again, you can apply AI to that, and machine learning and all the digital tools I spoke about. So thank you very much for that question.
Thank you. Just to lend my voice there, take the advantage of leading the questions. I know, or I guess, Ayo, that artificial intelligence completions has been around for quite some while now. So
Correct.
if we move it on, doing zonal isolations and all that with artificial completions, moving it from intelligent completions, moving it from intelligent completions to artificial intelligent completions wouldn't be a very big milestone. So I guess that's what you're presenting here.
Correct, yeah.
Okay. Thank you.
So I see a question here about power transmission. How can machine learning be applied to power transmission? So because my group used to support GE Power at the time, who make a lot of gas turbine for the US market and the US and the China market, we have applied AI and machine learning to operations of gas turbines as well. First to the treatment of the gas that comes in, also to the operations, then to the maintenance, and particularly the auxiliary components. So they're always, evaporators. You want to know what your steam regenerating system is doing, all those little components. So the whole power thing is almost like how you have an automobile engine where the pistons and all the main power generation is in the block, but you have different you have the radiator, you have the alternator, and all those things. So we also apply AI and machine learning to understanding the performance implications of all of those, and also to manage the system to make sure it's efficient. You have an efficient cooling, efficient heat regeneration and introduction, so that the gas you're introducing has already been preheated and all that. And also to ensure that the gas is dry enough, because when you have wet gas, the wet gas eats into your turbine vanes and sort of creates another problem on its own. So yes, machine learning can be applied to power generation and I just mentioned the gas to power generation part of things. I'm sure it can be applied to geothermal or hydro as well.
Thank you very much. Any major advances in the area of MWD and LWD with AI, measurement while drilling and logging while drilling, all that? Are there some major advances you could intimate us on?
So funny you mentioned that. We have a few systems that are in development, and again, it's around managing the amount of data. Within the North Sea, a lot of information has been collected, and there's an organization that has now harnessed all that data together and is trying to understand how we can learn from all the information. So there's a Clarity project that has been set up, which a few of my colleagues are working on. And what they're looking at doing is pre-modeling. So we understand the way the technology works, but in most cases, understanding what you are going to measure and the parameters or the limits of the parameters would help with your logging speed, would help with the size of the tool, would help with that. So there's a lot going on in the space of understanding the environments that we're going to be playing in, understanding the reliability of the equipment, because a lot of times you're drilling and your tool fails, you have to pull out a hole, or you have to continue drilling without drilling blind without one of the tools. If we can understand the environment, if we can predict pore pressure prediction, from the seismic, predict what the saturation is going to be like, what your losses are going to be like, then you can plan better, and then using the same tools. So it's not really developing any new tool, but it's more around the planning, the risk management, risk mitigation, that there is a current effort that I know about.
Thank you very much. So I think the final few minutes or so for anyone who wants to raise his hand now to fill in a question. we've taken the written questions. Otherwise, I'm going to be handing over to Emmanuel, and then for him to introduce the comments has been scheduled. In the absence of any other question, okay.
Yeah.
Over to you.
Thank you so much. I don't think there's any other question. Thanks so much, Engineer Sharp, for handling that session, and thanks a lot, Ayo, again for Engineer Ayo for the response. Just to reiterate again what the chairman had said earlier, we will be having you back. I have the express permission of the chairman to say that we'll be having you back again for the other parts, and more importantly, we would want to have you on a stakeholder sort of committee. We're already working on certain things like what someone said in the chat box already about transforming these ideas to academia and how to get a transition between industry and academia to get these things to use. We have something going on already, as the chairman mentioned, and we'll be inviting you to join in that discussion. We're looking at implementing it as soon as possible in Nigeria, and also form collaborations between the academia in the UK, in Nigeria, and also elsewhere. I'll be talking about our next webinar as well, which is looking at things like that. So we have all of this wrapped up already. We are in progress. We're working in that direction with other speakers who have come on our platform. And we're lucky to have you as well to join into that, if you don't mind. Hopefully the chairman will take on the discussion with you subsequently. So thank you very much once again. And we really appreciate your time with us. I would hand over quickly to the chairman to invite the dignitaries we have just for quick comments before we conclude. We still have about 15 minutes to finish up. So, chairman, sir.
Hello.
Yes.
Yeah. So yeah, I would like to invite the former NSA president, engineer. His goodwill message. Our past presidents are, and if you can unmute yourself, please, so that you give us your.
Thank you very much. I just did that. I'd like to congratulate, first and foremost, Ayo, and want to say that without any authority to back me up, it's already due for a professorship. So just keep it up. By the second edition, I'm sure we will have done more than it is necessary. So Daddy will confirm that. Let me congratulate Professor Ofi and Mommy. He probably should remember me. I'm the in-law to the very good friend, late Professor Daramola. My aunt is the wife. I remember taking his Pando Yam to the UK those days. My auntie was one of the major distributors. That's the kind of thing we should encourage these days. We need that. Our teachers, our lecturers doing a lot more of that as patent and more importantly, as businesses. I like to relate Glasgow branch, Shewan and the team, and see how delighted I am. The trajectory that our diaspora branches, Glasgow, Manchester, London is bringing in is quite heartwarming. I'm so glad with what I don't know, is it not the chairman, either the anchor or the other person, the publicity secretary, the amount of things they're doing. I've been very much involved in Manchester branch, and I'd like to confirm that the amount of dimension you're bringing is very heartwarming. For instance, Dr. Ngala, I also teach at the Lagos State Polytechnic. Dr. Ngala has given a webinar on KTV in my Polytechnic based on what we saw him doing. I mean, during the one in Manchester. And he would have been to my Polytechnic and other schools in Nigeria, but for COVID. I'd like to thank this very good drive from Glasgow branch and all the other branches. We need you more than ever. When I say we, that includes you, all of you in diaspora. This is when our brain drain should turn to real gain. I'd like to congratulate you all and thank you for the opportunity. Congratulate Professor Ofi and Dr. Mrs. Ofi. I'm sure you're very proud of Ayo. I'm very proud of him. That was fantastic. And we have a million and one Nigerians all over the world doing great things. We just need to remember that we owe it a duty to look back and contribute to our development and think less of all the negativities. Because for crying out loud, all countries, all committees have their own negatives. So thank you all for the opportunity. Please, I would like to be reminded of every webinar that comes up. I've learned a lot, and I also like to join you to propagate this ideal. Thank you very much.
Oh, thank you, sir. Thank you, past president. We appreciate you for joining us. And Vice President, while you are waiting, and I mean on the call as well, I want to introduce Professor Ofi to our platform tonight to give us his goodwill message. Thank you, sir. Prof, if you can unmute yourself, sir.
Thank you very much, the chairman of the Nigerian Society of Engineers, Glasgow branch. And thank you all my other professional colleagues. I must say I have enjoyed this teaching. Also, I want to thank Ayodele for the good presentation. That was very good. And also for fulfilling all my hopes. Basically, I'm a mechanical engineer, but just before Ayodele was born, I left Shell as senior reservoir engineer. And I also went back there in 1992 and 1994 as a consulting reservoir engineer. But Ayodele has gone much further, and I hope you will develop this much further and hand over to Tommy. That respect. Before I received this message this morning, and immediately I pasted it on the platform of the Nigerian Institution of Mechanical Engineers, so that my other colleagues will be able to benefit from it. And I think Dr. Adiaga probably got wind of it through that platform. The chairman Glasgow branch, I want to advise that during other meetings that will involve such things that will concern Nigeria, maybe you should let the Nigerian Society, the president of the Nigerian Society of Engineers, and also the president of Society of Petroleum Engineers in Nigeria to be aware of this, because you are doing very great things over there, but the direct application is here in Nigeria. And as you have said, a few of the Nigerian universities want to be involved in what you are doing. I thank you very much for this, and I think you should keep on the flag flying. God bless you all, and God bless Nigeria.
Thank us. Professor Ofi is our role model, is our dad, is someone to. We really appreciate you, sir. And engineer Mrs. Margaret Oguntala, as a former vice president of the NSA. Excuse me, ma, do you want to unmute yourself and message, ma? Thank you. Oh.
Thank you. Thank you, Mr. Chairman. Actually, I joined this program a bit late, maybe about 10 minutes late, but all that I heard about that lecture, it was fantastic. And like somebody remarked earlier, it was a world-class lecture, one that anybody cannot afford to miss. So this webinar is not just an eye-opener, it's not just illuminating, it's also very, very educative. And I congratulate the guest speaker, Dr. Ayo Ofi. You know, you spoke like a professor. I was just kind of overwhelmed. And I'm not surprised after I heard from Professor Ofi, that you were born into engineering. So nothing less is expected of you, really. And thank you for making Daddy proud. You know, I know the feeling of pride that you feel in your child when the child has fulfilled this purpose. And I pray that you continue to move from height to height. And I congratulate Glasgow branch for this. You know, this is one of the benefits of COVID, as I would say, because Zoom meetings is kind of a fallout of the COVID-19. And look at me here in Lagos, joining Glasgow. So I just told a friend a few moments ago when he called me, I said, look, I'm in Glasgow. And he thought I was actually physically in Glasgow, but I am in Glasgow, you know? So we thank God for technology. And the fact that the branch is taking this strides to ensure that we're all informed and educated is quite commendable. And then I will also say that many of us now, I mean, this kind of lecture, you would normally have to pay for it, and we're getting it for free. So I thank Glasgow branch, really. I really am very grateful for this lecture. And I hope that you continue to grow from strength to strength. Thank you very much. But please, before I leave, let me just greet my past president, Engineer Ademola Olorunfemi, and other elders that are here. I've already greeted Professor Ofi somehow. So, executive committee members of Glasgow, congratulations for this, and we pray for more. Thank you.
Oh, thank you, Ma. Thank you. Thanks for joining us. We appreciate you. I will now hand over back to Dr. Emmanuel Salifu just to continue with the program. Thank you.
Thanks very much, Chairman, and thanks to all our dignitaries for your comments and goodwill messages. Just to say that I think Engineer Ayo should be proud of himself today. Daddy actually gave him a score, very good, and that was impressive. So it's quite difficult to get that kind of score from Daddy. So congratulations for that. I'll just go on down to the announcements, and then we wrap up. So I mentioned earlier that we're working on lots of things at the branch level, and one of them is what will be happening in our next webinar. Well, sort of webinar, I would call it still, but what we're having next in May is a semi-mini symposium, if you will. So we'll be talking about professional engineering in the UK and in Nigeria. We're looking at the education, the licensure, and the practice. And we have a very wonderful lineup of guests who will be addressing this, discussing with us. The International Affairs Manager from UK Engineering Council will be with us, Dr. David Clark. The Registrar of COREN will be around, Engineer Professor Joseph Odigure, and the Executive Secretary of the NSC, Engineer Okopi Momo. We're bringing them all to discuss about how to begin to have some relationships between the sister bodies in the UK and in Nigeria, the regulators, the society, and the UK Engineering Council, to discuss and share notes on best practices globally to help each other grow as mutuals in the table of discussion for development in engineering. And we'll be talking about engineering professional registration in the UK, professional registration in Nigeria for engineers in the UK and abroad, and things like that. So invite everybody as much as possible, people from the academia, from industry, people who are students looking forward to getting registered, people studying in the UK, working in the UK. This is open to all. So we hope that you have you present the next one. It's on Saturday, the 15th of May, and it's 5 p.m. 5 p.m. British summer time is the same as 5 p.m. in Nigeria. So it's the same time, 5 p.m. on Saturday, 15th of May. You can put that on your calendar. The flyers and other details will be shared through our various platforms soon. And also just to mention, our sister branch, the Nigerian Society of Engineers Manchester branch, will also be having their April general meeting and technical session next Saturday, no, 2 Saturdays from now. That's Friday. Oh, sorry, Friday, the 30th of April. Friday, the 30th of April is their next general meeting and technical session. The title is Invention and Patent, and their speaker is Engineer Olanrewaju Aluko. They are addressing the theme of capacity building and innovation management, and the details are there on the flyer and will be distributed across different platforms as well. Finally, I'll just following our ritual, I'll call on the secretary of the branch. We still have 5 minutes, but I'll give him 2 minutes to say words of appreciation to our guest speaker and all who have attended this event. Engineer Charles Okafo, the branch secretary, over to you.
Thank you very much, Dr. Emmanuel, and a very, very, very big applause and thanks to our engineer, Ayo. I can see that everybody is quite happy from Daddy and the Engineering Society at large. It's a very nice presentation, and I believe this would have taken some chunk of time for you to put them together. So we really, really appreciate. Thank you very much, and we still look forward to having you, coming in to give us another wonderful presentation. Also, I want to particularly thank each and every one of us that is here. Prof, thank you very much for making our time to see what we are doing here. Our past president, we thank you very much. Every member of the society that are here, we thank you. And particularly, I won't fail to thank our mommy. I was a bit surprised when Dr. Shehu said that Ayo's mom was here, and it brings up one of these items that was sent on my WhatsApp. And what was it? A young child that was crying, refusing to go to school, and then the mother was behind with a cane. There is this type of cane that when you bend it, it doesn't break. So, and what the woman was doing was trying to send the child back to school to go to school. And then what was the lesson there? The person that sent the WhatsApp said that behind every successful man, there is a woman. And then he now said that that woman is not the wife, but the mother. So, so it's a lesson that she has been there. And then today we all see what he has turned to. So a very big thank you for the work you have done as a mother to get this young man to where he is today. I can't say more than that. And to our friends, and the heads of different NSC branches. I think I saw Dr. Bosu, Engineer Bosu. Thank you for being on board here. We all welcome you, appreciate your presence, and thanks everybody. Over to you, Dr. Emmanuel.
Thank you very much, Engineer Charles, for that brief, very well captured appreciation. So as promised, here are links to all the avenues with which you can reach out to us. The Glasgow branch of the NSC is very open, and we are at the forefront of innovation. I like to say we're probably still the youngest branch, but we want to really do bigger things with everyone. So you're welcome on board. You can reach us on Twitter. Our handle is there at NSC Glasgow. On YouTube, this very video should be on YouTube later tonight, so you can access it, share it with as much people as possible to gain from the knowledge. We also have videos of all of our talks, all the webinars we've had so far since August last year. They're all there. You can access any of them for free. And you can send us an email if you would want to discuss further on any other thing at all that you think we can partner together with. And we're on Facebook. And that's our website. The website is looking really great, so we're enjoying you to get on and engage with us as much as possible. And with that, I see a hand up. I don't know if that's something urgent.
Yes, please. Just one sentence.
Okay.
Thank you very much, Emmanuel. Just to confirm that you are
all right, yeah.
youngest, but you are twins, Manchester and Scotland, and Glasgow, and you are doing great. Two brilliant twin. I don't know if you are brothers or sisters. Please keep it up. You've actually given London a wake-up call, and they're up and doing now. I'm glad to say that. So again, congratulations. Thank you for the opportunity to chip in this again. Bye for now.
Oh, yeah, thanks very much. Thanks for that. Yeah, thank you so much. So yes, we're working in collaboration with our sister branches, NSC Manchester, as the president has said, our twin branch, okay, NSC Manchester and NSC London, and we're all doing our best to have the development strides going on abroad brought into Nigeria, inject into the system, and share notes, as we've said, and this will get it to its heights at the next event we're organizing. So we invite you all to be there to discuss these very issues. So thank you very much again for your patience and for being around up to this moment. From me and from us on behalf of the Executive Council members of the NSC Glasgow branch, we want to say have a very good evening and thank you so much. Hopefully we'll see you again at the next event. Thanks and bye-bye.
Thank you.
Thank you. Bye.
Bye-bye.
Bye.
Bye-bye. Thank you.
Congrats.